Hi everyone. So in chapter 10 we're going to be talking about partial differential equations in Fourier series. A partial differential equation is an equation of several variables and its derivatives. And so before we can really get started solving our first PDE, we need to do a little bit of a groundwork. And we're going to start in section 10.1 talking about two-point boundary value problems. So let's start talking about two-point boundary value problems. Remember that when we used to solve initial value problems, we're usually given an ODE of the form y double prime plus p of t times y prime plus q of t times y equals to g of t. And we were given initial conditions, for example, y of t of naught equals y naught and y prime of t naught equals y prime naught. So usually we were given two initial conditions in the same point, in the same t naught here. And graphically it would look something like this, if we were to graph this. So this is t and this is the graph of our solution. Usually we're given an initial point t naught, and we're given also a corresponding y value for this t naught, and we're also given the value of the slope. So this is the slope y naught prime. This is how we usually used to solve initial value problems, but when we're solving two-point boundary value problems, here's what it's different. So here's what's different when we're solving two-point boundary value problems. We usually have the same y double prime, plus p of t, y prime plus q of t times y equals g of t. And we're also given two initial conditions, but these are y of alpha is equal to y1 and y of beta is equal to y2. So, and this is because it happens a lot in physical situation. That's why we can also solve, like, for our initial value conditions using two-point boundary value problems. So graphically it would look something like this. You would have your solution, and you have your two values of t here, alpha and beta, and you would have corresponding values in the solution, y1 and y2. And it's going to become clearer when we solve our first example. So let's go ahead and do an example of that. So let's go ahead and solve this problem right here. We have our differential equation, y double prime plus y equals 0, and we have our two initial conditions. Here we can see that these two initial conditions are not given at the same point, so that's why we're doing a two-point boundary value problem. But we start solving it the same way we used to in the other one. We'll start by writing our characteristic equation. So characteristic equation is r squared plus 1 is equal to 0. So r is equal to plus or minus I. If we subtract 1 on both sides and take the square root, it's going to be the square root of -1. That's why it's the square root of plus or minus the square root of I. So we have this. In order to write our solution to our the general solution, so the general solution will be this. We'll have y of t is equal to c1 e to the 0 cosine of t plus c2 e to the 0 sine of t. This e to the 0 is here just to, like, show, because we're doing, like, we have complex roots. Even though the real part is 0, I'm just putting this in case, like, we do an example that it does have a real part, that we don't forget to put our e to the 0s. But since e to the 0 is just 1, this is going to go out. I just think it's important to put it there in case we have a real part in the future. But in this case, we only have our pure imaginary plus or minus I. So our general solution is going to be C1 cosine of t plus C2 sine of t. All right, and now we're given these two initial conditions. So we'll start by doing the left boundary condition. So the left boundary condition is y of 0 is equal to 0. So y of 0 is equal to 0, and cosine of 0 is equal to 1. It's going to write this down, cosine of 0 plus sine of 0. We know that sine of 0, I'm missing my constants here, C1 and C2. We know that sine of 0 is just 0, so this goes out, and cosine of 0 is equal to 1. So therefore, C1 is equal to 0. Alright? Now, what about the right? What about the right boundary condition? The right boundary condition is just that C prime of 2 pi is equal to 1. Well, let's first take the derivative of our general solution. So the derivative of our general solution is y prime of t is equal to negative C1 sine of t plus C2 cosine of t. That is our derivative of our general solution. Now, if we evaluate it at the point given, namely 2 pi, y prime of 2 pi is equal to negative C1 sine of 2 pi plus C2 cosine of 2 pi. So the sine of 2 pi is equal to 0, so this term goes out, and the cosine of 2 pi is equal to 1. So this term is equal to 1, and this is equal to 1. So therefore, C2 is equal to 1. So we found our constants C1 and C2. What we need to do now is plug it back into our differential equation so that we'll have our solution to our initial two-point boundary value problem. So thus, solution to BVP, so the boundary value problem, is y of t, C1 is equal to 0, so we're just left with sine of t. So this is our solution to our boundary value problem. And if we want to look at this graphically, let's make a graph of our solution and see where these came in. So if we graph y equals sine of x, yeah, it's not that symmetric, but this will do. So this is y equals sine of t, actually. So we have t here. So we know that y of 0 is equal to 0. That is our first initial condition. So we're given this point here, and y prime of 2 pi is equal to 1. So we're also given this slope here. So this is how we connect these informations. Like we do the characteristic equation and solve the problem normally, but then we use our boundary value condition, our initial boundary value problems, or boundary conditions, to find the solution to our BVP. Alright guys, so that's it. So on the next video I'm going to do more examples of boundary value problems and how to solve them. Alright, I'll see you next time.